Hey everybody, I hope you're still doing well out there. Um, we are getting pretty close to the end of the school year, so keep up the hard work. I know I'm throwing a lot at you. I'm asking you to walk the walk and talk the talk of being a chemist. So keep sending the questions my way. As you have them, we're going to add two layers of complexity to what we started last week, ionic compounds and synthesis reactions. Today we're going to talk about polyatomic ions and single replacement reactions. So a couple learning objectives for you. First of all, I can write formulas of neutral ionic compounds that contain polyatomic ions. I'll define what those are in just a second. And secondly, I can predict the products of single replacement reactions, which is another type of reaction like synthesis reactions, a little more complex. All right, so what is a polyatomic ion, you might ask? Polyatomic ions are ions made up of many, that's what the prefix poly means, atoms of different nonmetal elements. So a polyatomic ion is a many-atomed ion. Ionic compounds with polyatomic ions form under the same rules that we've practiced last week with the, or in the last lesson with the simple ionic compounds. The trick is to treat the polyatomic ion as a single packet that always has the same charge, just like cations and anions of elements do. There are many polyatomic ions out there. Each has their own name, their own formula, their own charge. Here are some of the more common ones. We have the ammonium ion, which is a nitrogen with 4 hydrogens and has a +1 charge. The nitrate ion, a nitrogen with 3 oxygens and has a -1 charge. The sulfate ion and the phosphate ion. So again, many atomed ions that have a constant charge is a polyatomic ion. So for the sake of this class, I'm going to give you a pretty small, simple list of polyatomic ions that we're going to play with. Again, there's hundreds out there, but these are some of the big ones, the most popular. We have ammonium is the only polyatomic cation that we'll deal with. It's got the formula NH4 and has a +1 charge. Hydroxide has the formula OH and has a -1 charge. Nitrate has the formula NO3 and has a -1 charge. Sulfate has the formula SO4 with a -2 charge. Carbonate has the formula CO3 with a -2 charge. And lastly, phosphate has the formula PO4 with a -3 charge. Again, those are the big ones that we'll deal with in this assignment. And the key piece here is everything you've already learned about ionic compounds still stands. Don't get thrown off by the fact that these ions have multiple elements. The key piece here is to treat each polyatomic ion as just a single packet, a single thing, like we did in the previous when we were dealing with sodium with a +1 charge, or chlorine with a -1 charge. So when it comes to writing ionic compound formulas and names with polyatomic ions, we're going to use the same process as before to create neutral ionic compounds. Can't stress that enough. Overall, the compound must have its charges balanced. Positives must cancel out negatives. But the key now is to treat the polyatomic ion as a single packet. You can start by adding your cation and your anion with the charge, even if one's a polyatomic ion. And then you're going to ask yourself, is it balanced? If not, you're going to add whatever you have less of, either positives or negatives. And you'll keep doing that process until you try to make the overall formula, the overall compound become balanced. And then you count up how many cations and anions you had to add to create a neutral ionic compound, and you write the formula. Now, a trick here is we're going to introduce the idea of parentheses. So if you added multiple polyatomic ions, put the polyatomic ion in parentheses and add the number as a subscript outside of the parentheses. I'll do an example in just a minute. When writing the names of ionic compounds with polyatomic ions, we use the polyatomic ion name without any changes to the ending. What I mean by that is we'd use these names right here. So let's look at some examples of this. Let's say I want you to form a compound using a sodium ion and a nitrate ion. The sodium is Na, and it's going to have a +1 charge, and I know that because I look at the periodic table and it's in the first column. Nitrate is NO3. I know that because I referenced this table back here, and it's right here, nitrate, NO3. And I also know it's got a -1 charge. So there are my two ions, my cation of sodium and my anion of nitrate. And then I ask myself, is it balanced overall? Well, yes, the +1 of sodium cancels out the -1 of the nitrate. So it's already balanced. So my formula would just be NaNO3. In other words, 1 sodium cancels out 1 nitrate. You don't have to add any extra subscripts. And if I were to read the name of that compound, I would say that that is sodium nitrate. Here's another example for you. Let's say I ask you to form a compound with calcium and hydroxide. Calcium is just a lone element on the periodic table. I look at its location. It's in the second column, so it's got a +2 charge. Hydroxide, on the other hand, is a polyatomic ion. So I look at my table, and I'll paste that table into your assignment. And I see that hydroxide has the formula OH with a -1 charge. And I ask myself, is this balanced as it stands right now? And it's not. I have more positive than I do negative, so I have to add another polyatomic ion to add the number of negative charges I have. So I'm going to add on another hydroxide, and now I ask myself, is it balanced? And in this case, yes, it is. The +2 of 1 calcium ion cancels out the total -2 of 2 hydroxide ions. So when I add up the total negative charge is -2. So now I've reached the point where it's balanced. And now when I go to write the formula for this, I say, okay, I'm going to have 1 calcium and I'm going to have 2 hydroxides. And this is where it gets a little tricky because I have 2 hydroxides, and hydroxide is this one packet of OH2. I need to put hydroxide in parentheses. So this is how I would write that formula. Ca with no subscript because I only needed 1. And then OH, and since I needed more than 1, I would have to put that OH in parentheses with a 2 on the outside. And I would read this compound as calcium hydroxide. One thing I would want to know up here, say I wanted to do calcium nitrate, Ca with a +2 charge, and nitrate, NO3 with a -1 charge. When I went to do that, I would see that I need to add 2 nitrates to get to a total negative charge of -2 to cancel out the +2 of calcium. And so when I go to write this, the NO3 would stay in the parentheses, and the 2 would fall outside. What that means is I needed 2 NO3s to balance. This undoubtedly will probably leave you asking some questions. Feel free to use your resources, look online. There's lots of videos on this. Send me emails, send me texts, ask questions in Google Meets. This is definitely something that comes with practice. All right, so that's the P section of the assignment, is trying to write neutral ionic compounds that contain polyatomic ions. Do the best you can with that. The PD section throws at you a more challenging type of reaction. Last week, or last assignment, we talked about synthesis reactions. Now we're going to talk about single replacement reactions. Single replacement reactions happen when a solid metal element reacts with an ionic compound dissolved in water. So here in this general form, what I have is element A plus compound BC is a single replacement reaction. And in these reactions, the lone metal, the element, ionizes. It'll lose electrons, and it'll replace the cation in the compound with the anion. So A jumps into this compound to create a new compound, AC, And when it does that, it kicks out B as its own element. So B comes out as its own element, and AC is the new compound formed. The newly formed ionic compound might have a different, will have a different formula than the reactant compound because the metal's ion charge might be different. So here's what I mean. In this particular example, I'm using D block elements, so I won't give you an example like this. But here we have a solution of silver nitrate. That's this compound. Ag is silver, NO3 is nitrate. By the way, silver has a +1 charge. So a solution of silver nitrate has a copper wire added to it. So that's just elemental copper, a solid. And when this happens, the reaction that will occur is you're going to have the copper replace the silver in the compound, and the silver is then kicked out as an element. And so here's what I end up with. This fuzzy stuff is actually elemental silver as a solid, and then the solution turned slightly blue because a new compound formed in solution, and that compound is called copper nitrate. And when this reaction occurs, you wouldn't know why, but I'll just tell you that copper is going to take a +2 charge. Again, it's in the D block, so I can't determine that just from the periodic table. But I'm telling you, it's going to take a +2 charge. And so that's why the overall formula here is going to be copper, it's going to be CuNO3 2, because I need 2 nitrates at -1 apiece to cancel out the 1 copper at +2. Again, this is a skill that we'll just need to practice and get feedback on as we go, but hopefully me doing some examples will help. So here are a couple examples. The first one is calcium reacts with sodium chloride. For the sake of simplicity, I got rid of the phases. So I dropped the solid, the S in parentheses, and I dropped the AQ, aqueous or dissolved in solution. And we're just going to focus on the fact that here we have an element reacting with a compound. And remember, the cation of the compound is going to switch spots with the element. That's the replacement that occurs here. So let's see what we get here. Ca and Na will switch places, the two metals. Na +1 will become Na by itself. So when I pull Na out of the compound, I get just the lone sodium as an element. And then Ca will ionize to Ca +2. How do I know that? It's because I'm looking on the periodic table and calcium is in the second column. And it will bond with Cl -1 because of chlorine's location in the 7th column to make CaCl2. How did I get that formula? It's going to take 2 chlorines to cancel out the +2 charge of calcium. Or again, I could just do the crisscross method and take Ca's +2 and bring it down as chlorine subscript, and Cl's -1 and bring it down as calcium subscript. So there is my new compound that's formed, and I would write my total reaction as Ca plus NaCl creates Na plus CaCl2. And if you care to see it, I know some of you probably will, when I put the phases back in, need that to go away again, I would read it as Ca with an S plus NaCl with an AQ yields Na with an S plus CaCl2 with an AQ. Ultimately, that means solid calcium reacts with aqueous sodium chloride to produce solid sodium plus aqueous calcium chloride. I know this is like learning a new language, so please be patient with yourself. We'll go through a couple more examples, and hopefully the more you practice this, the more you'll pick it up. All right, so let's do another example. Here I've got aluminum reacting with magnesium nitrate. Magnesium is in the second column, so it's got a +2 charge, and nitrate, NO3, has a -1 charge. That's why I need 2 NO3s to cancel out the 1 Mg. And here you can see that I put the NO3 in parentheses with the 2 on the outside to indicate I'm talking about 2 nitrates. So what's going to happen here is first I recognize single replacement reaction, element plus compound, and that aluminum and magnesium will switch places. The two metals swap spots. Mg plus 2, the cation in the original compound, will come out as Mg by itself, and I can write that. I've got Al plus MgNO3 yields Mg plus, and now I have to figure out what this new compound is going to be. And I know that aluminum will ionize to +3 and bond with the NO3 -1 to make a new compound that is AlNO3 3. Why do I have that 3 out there? That's because I need 3 nitrates or 3 NO3s at -1 apiece to cancel out the +3 of the 1 aluminum. So in total, what do I get? This is the reaction. Al plus Mg NO3 2 yields Mg plus Al NO3 3. And again, you can see it over here with the phases written in if you're curious to include your phases, your solid, liquid, gas, aqueous. Hopefully it's starting to make sense that all you're doing is switching the cations, switching the metals, and figuring out what the new compound will be. One more example. Here we have barium reacting with, that's actually hydrochloric acid, but if you thought hydrogen chloride, then that would be a pretty appropriate thing to name that right now. And what's going to happen here is barium and hydrogen will switch places, the two cations. H plus will become H2. Why H2, you might wonder? That's because hydrogen is a diatomic element. So if it's coming out to be just an element by itself, not bonded to anything else, then it has to come in a pair. That's kind of a nuance, but chemistry is built on nuance. And it's also a gas. That's, again, just something that over time you'll memorize. So what did I do? I pulled out the H from the compound, and I get H2, again, because it's diatomic. And then I asked myself, what's the compound going to be that forms? And Ba will ionize to Ba plus 2 because it's in the second column of the periodic table. And it will bond with the chlorine with a -1 charge to make BaCl2. Ultimately, what I'd write for my final reaction is this. Ba plus HCl yields H2 plus BaCl2. And then again, including the phases and recognizing that hydrogen's a gas, I get the full reaction over here. So hopefully that started to make sense. If you're up for the PD challenge, you can give this a shot. And again, certainly shoot me questions as you have them. We're going to add just one more layer of detail here, and that is called the activity series. Some of the examples that we just did, some of the example reactions, were theoretical only. I kind of just picked a metal and made a compound and said, what would happen if these things were put together and able to react? But in actuality, not everything can react. So to determine if a single replacement reaction would occur, you must use the activity series. And here's the activity series. It's just a list of elements. And this is how we use it. Any solid metal on the activity series can replace any cation below it in an ionic compound. If the solid metal reactant is below the cation, so if the element is below the cation in the compound, there will be no reaction. I think, again, this will be something that it'll be helpful to see some examples and hopefully come together. So let's go through a couple examples. We just did these examples in the last set of how do you write single replacement products. Here, when I have calcium, that is my metal, and I'm wondering, can calcium actually replace sodium in this compound? And to figure that out, I look over on the activity series, and calcium is above sodium, which means calcium is more reactive than sodium. And so therefore, I would say, yes, calcium can replace sodium in the activity series. So this reaction will proceed as we predicted in the previous slide. Again, in this example, the metal calcium is above the cation sodium, so the reaction is able to occur as described. Let's do another one. Here my metal is aluminum, and my cation in the compound is magnesium, and I'm asking myself, is aluminum more reactive than magnesium? Is aluminum above magnesium? And when I come over here to my activity series, I see that magnesium is above aluminum, not the other way around. And so in this example, this reaction would not actually occur. In this example, the metal aluminum is below the cation sodium. Oops, that's supposed to say magnesium. Sorry about that. That's supposed to say magnesium. So the reaction is not actually able to occur. And so what I would ultimately write in actuality for this is something like this. Al plus MgNO3 2 yields no reaction. These products are not able to form because aluminum is not more reactive than magnesium. So there you have it, ladies and gentlemen. I don't think I have anything left. That was another video full of a bunch of information. It's definitely, I think, getting a little harder. So please, as you try to figure out, how do chemists talk about what they do, please just stay in touch and ask questions as you have them. And other than that, I will catch you on the flip side. Be well, guys. See ya.